This is the MCAT Intensive Review brought to you by In Time TV. I'm Dr. Gangarel. We're in the Physical Sciences section, the Physics subsection. The chapter is Waves and Periodic Motion, and the topic of this video clip is Simple Harmonic Motion. A PDF will pop up during the break, which you can print out, annotate, review as much as you like during the course of the lecture or afterwards.
The engine is connected to the tool. The tool is connected to the hand. The hand is connected to the body. The body is connected to the mind. The mind is connected to the heart.
Simple harmonic motion. Objects which obey Hooke's law, the law that describes the linear relationship of force and displacement on a spring, will oscillate in simple harmonic motion when perturbed from their equilibrium point. Now this sounds very technical and very specific, and you might say just springs. We don't see a lot of springs in the world, but in reality a lot of objects have spring-like behavior. Namely, they undergo a linear deformation when pressed or pulled or pushed, etc. And if they have this property of having this linear relationship, if they are in equilibrium and you press on it, then it will oscillate around that equilibrium position in simple harmonic motion. Hence, simple harmonic motion has near universal applicability to many physical phenomena, not just springs. Of course, in physics, as well as in a lot of medicine, we study things in a simplified form, hence simple harmonic motion, and can then derive implications for more complex phenomena. And we'll actually do that during this video clip. So this oscillation of simple harmonic motion can actually be broken down into three descriptive parameters or variables, and these are the amplitude of that motion, how big it is, the frequency of that motion, how frequent it is, and the phase shift, whether we're starting from the equilibrium point, away from the equilibrium point. As soon as we take a snapshot and look at that motion, where are we starting in the wave of motion? That's the phase shift. So let's look at the features of simple harmonic motion from a physics standpoint. First of all, force and acceleration are in the same direction. So if you have an object and you perturb it away from that equilibrium position, the force will be back to the equilibrium position. The acceleration is back to the equilibrium position. Notice that the force and acceleration are opposite to the displacement. If you pull it out here, the force is pulling it back towards the equilibrium position, but notice you pulled it away from the equilibrium position. So the force and acceleration are opposite to the displacement vector. The force and acceleration are maximum at the maximum amplitudes. If you pull it away here, the force is maximum. There is actually no force when you're at the equilibrium position. However, the velocity is a maximum at the equilibrium position. So it's oscillating back and forth. Actually, at the end point, it's zero as it reverses direction, and it accelerates in its maximum velocity at the equilibrium point back and forth. Let's look at that diagrammatically. Here is a spring attached to a fixed wall with a block. Here's the equilibrium point, and you've pulled it away, and it will oscillate around the equilibrium point like this. Everyone knows that's what springs do. And this is the maximum point, which is the amplitude, and we can convert that back and forth motion. It turns out, because of Hooke's law and differential equations, which you don't need to know the derivation, but if you go through that, F equals minus kx, Hooke's law, implies this equation, which is a very familiar trigonometric equation. You'll see in your textbook sometimes sine function or cosine function. Recall that the sine function is 90 degrees or pi over 2 radians phase shifted from a cosine function. So the fact that it's a sine function or cosine function is actually irrelevant. It really means you have a different phase shift. For the purposes of our notes here, we use a cosine function. What this tells you is that the x, the displacement away from zero, the equilibrium point, is equal to the amplitude times the cosine of 2 pi times the frequency times the time plus the phase shift. Notice those three parameters that I mentioned at the outset. The amplitude defines the equation, the frequency is a variable in the equation, and the phase shift is a variable in the equation. And this is a trigonometric equation. Now let's look at the implications of this. If you further solve that equation, and you don't need to know the derivation, but you do need to know these implications, the frequency of any spring, a perfect spring, a Hooke's law spring, is equal to 1 over 2 pi times the square root of k, the spring constant, over m. So let's look at a spring. If you have a very tight spring with a high spring constant, of course, if it's very tight, it will oscillate in simple harmonic motion with a high frequency. That's because the k is in the numerator here, and the frequency actually will be proportional to the square root of that spring constant. Very tight spring means a high frequency. On the other hand, if you have a very heavy spring with a heavy mass, m, sitting there, actually the frequency will be lower. That's because the mass is in the denominator, and you have a lower frequency. You can generalize this phenomenon to the concept that very tight objects, strongly bound objects, objects that have a lot of interconnected, intermolecular, for example, forces, will tend to have high spring constant and tend to oscillate with high frequency. Another corollary is very large objects tend to oscillate with low frequency. If you look at a huge bridge, for example, and bridges have resonant frequency, they actually have a low resonant frequency. In fact, some bridges have a resonant frequency that is equivalent to the frequency of walking, which is why soldiers, when marching on a bridge, are instructed to march out of sequence so that you don't set up a resonant frequency with that bridge and the bridge collapses. So again, these are some generalized conclusions from the simple harmonic motion that is characteristic of Hooke's law defined spring systems. So in summary, objects which obey Hooke's law, the linear relationship of displacement to force in a spring, will then mathematically have been shown to follow simple harmonic motion. In fact, many objects have this sort of characteristic that they will oscillate when perturbed from equilibrium. That simple harmonic motion can be defined by three parameters: amplitude, frequency, and phase shift, and those all fit into a trigonometric equation defining the shape of that simple harmonic motion as a sinusoidally oscillating wave. This concludes the video clip on simple harmonic motion.